Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on complex analysis, power series lecture number 6, in which I will prove some theorems on power series. Now we prove a theorem. Theorem is the power series Gz equal to sigma n equal to 0 to infinity n a n z to the power n minus 1 obtained by differentiating the power series fz equal to a n z to the power n has the same radius of convergence as original series sigma a n z to the power n. Now we prove this. Let original power series is fz equal to sigma a n z to the power n. Let the radius of convergence of this power series be r. Therefore, 1 by r equal to limit n tends to infinity modulus of a n to the power 1 by n. This is number 1. The derived series be sigma n a n z to the power n minus 1. Let this is gz. Let r prime be the radius of convergence. Let this is number 2 of 2. Therefore, 1 by r prime equal to limit n tends to infinity n a n to the power 1 by n. This equal to limit n tends to infinity modulus of n to the power 1 by n multiply modulus of a n to the power 1 by n. This is equal to limit n tends to infinity. We may write this n to the power 1 by n since n is non-negative. Multiply limit n tends to infinity modulus of a n to the power 1 by n. This is equal to limit n tends to infinity n to the power 1 by n multiply using 1. This is 1 by r. Let this is number 3. Since by Cauchy's theorem we know limit n tends to infinity a n to the power 1 by n equal to limit n tends to infinity a n plus 1 by a n. Let this is number 4. Implies that limit n tends to infinity n to the power 1 by n equal to, in place of a n, if we write here n, then right side will be limit n tends to infinity. In place of a n plus 1 we will write n plus 1, and in place of a n we write n. This equal to limit n tends to infinity 1 by n plus 1. Using limit n tends to infinity, this will be 0 plus 1 equal to 1. Let this is number 5. Using 5 in 3, we get 1 by r prime equal to, here limit n tends to infinity, n to the power 1 by n, which is equal to 1 in 5. 1 multiply 1 by r implies that r prime equal to r. Therefore, radius of convergence of derived series is equal to the radius of convergence of original series. Proved. Now we define some function of a power series. If power series sigma a n z to the power n is written as fz equal to sigma a n z to the power n, then fz is called the sum function of the given power series. Now we prove the next theorem. Theorem is if fz equal to sigma a n z to the power n, then the sum function is an analytic function for every point within the circle of convergence of the power series. Now we prove this. Prove. Let fz equal to sigma a n z to the power n be a given power series. Fz is called the sum function of the given power series. Let r be the radius of convergence of the given power series. Let this is circle of convergence, center be 0 and radius be r. Let z be a point. Let z be a point inside the circle of convergence, and z plus h, let this is z plus h, be another point inside the circle of convergence. Let us draw a circle by dotted line such that the radius of this circle is rho and z comma z plus h points lie inside the circle. Therefore, modulus of z less than rho less than r and modulus of z plus h less than rho less than r. The derived series be sigma an multiply n z to the power n minus 1. We know that the radius of convergence of derived series is same as the radius of convergence of original series. Let the derived series equal to gz. Let this is number 1, this is number 2, this is number 3, this is number 4. From 2 and 3 we get that z and z plus h points are in the domain of convergence. Now f z plus h minus f z by h minus g z, this equal to f z plus h, since f z is sigma an z to the power n, so here we get sigma n equal to 0 to infinity an z plus h to the power n minus fz is sigma n equal to 0 to infinity an z to the power n by h minus gz is n equal to 0 to infinity n an z to the power n minus 1, and this will be equal to sigma n equal to 0 to infinity an z plus h to the power n minus z to the power n by h minus here n z to the power n minus 1. We may write this as sigma n equal to 0 to m is a positive number, an z plus h to the power n minus z to the power n by h minus n z to the power n minus 1 plus sigma n equal to m plus 1 to infinity. Here we take 0 to m, here m plus 1 to infinity, that is n equal to 0 to infinity an z plus h to the power n minus z to the power n by h minus n z to the power n minus 1, taking modulus in both sides, we get modulus of fz plus h minus fz by h minus gz. This is less than equal to sigma n equal to 0 to m modulus of an z plus h to the power n minus z to the power n by h minus n z n minus 1 modulus plus sigma n equal to m plus 1 to infinity modulus of an z plus h to the power n minus z to the power n by h plus sigma n equal to m plus 1 to infinity modulus of an n z to the power n minus 1 implies that modulus of fz plus h minus fz by h minus gz modulus and less than equal to s1 plus s2 plus s3. This is number 5. Number 1. Since S3 equal to sigma n equal to m plus 1 to infinity modulus of an n z n minus 1, since we know that the radius of convergence of the derived series is same as radius of convergence of the original series. Therefore, sigma n equal to 0 to infinity an n z to the power n minus 1 converges in the domain of convergence of the original series. Therefore, sigma n equal to m plus 1 to infinity modulus of an n z to the power n minus 1 tends to 0, that is less than epsilon by 3, where epsilon tends to 0. Therefore, S3 less than epsilon by 3. This is number 6. Number 2. Since S2 equal to sigma n equal to m plus 1 to infinity modulus of an z plus h to the power n minus z to the power n by h. Here we take bracket. This is number 7. We know that a to the power n minus b to the power n by a minus b equal to a to the power n minus 1 plus a to the power n minus 2 multiply b plus a to the power n minus 3 multiply b square plus dot 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 plus b to the power n minus 1. Therefore, z plus h minus z to the power n by h equal to z plus h to the power n minus z to the power n by z plus h minus z, and using this formula we get z plus h to the power n minus 1 plus z plus h to the power n minus 2 multiply z plus z plus h to the power n minus 3 multiply z square plus dot 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 plus z to the power n minus 1 implies that modulus of z plus h to the power n minus z to the power n by h less than equal to modulus of z plus h to the power n minus 1 plus modulus of z plus h to the power n minus 2 multiply modulus of z plus modulus of z plus h to the power n minus 3 multiply modulus of z square plus dot 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 plus modulus of z to the power n minus 1. This is less than equal to, since modulus of z plus h less than rho, we have already seen this. So rho to the power n minus 1 plus this is rho to the power n minus 2 multiply modulus of z is also less than rho plus dot 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 plus rho to the power n minus 1. This rho to the power n minus 2 multiply rho to the power 1. This is also rho to the power n minus 1. And this is equal to, this n terms, n rho to the power n minus 1. This is number 8. Implies that modulus of an z plus h to the power n minus z to the power n by h less than equal to n modulus of an rho to the power n minus 1 implies that sigma n equal to m plus 1 to infinity modulus of an z plus h to the power n minus z to the power n by h less than equal to sigma n equal to m plus 1 to infinity n a modulus of an rho to the power n minus 1. This is number 9. Since rho is less than radius of convergence, therefore the derived series converges for modulus of z equal to rho, that is sigma n equal to 0 to infinity n an rho to the power n minus 1 converges implies that sigma n equal to m plus 1 to infinity modulus of an z plus h to the power n minus z to the power n by h less than epsilon by 3 implies that S2 less than epsilon by 3. This is number 10. Now, number 3. Since z plus h to the power n minus z to the power n by h tends to n z n minus 1 as h tends to 0. This means an z plus h to the power n minus z to the power n by h minus n an z to the power n minus 1 modulus. This is less than epsilon n. Epsilon n is a very small quantity. Now we use the sigma n equal to 0 to m. Here each term less than epsilon 1, epsilon 2, epsilon 3. So here we write epsilon 1 plus epsilon 2 plus epsilon m. Here sigma. For this sigma we get here m number of epsilon. Let epsilon k be the maximum of epsilon 1, epsilon 2, epsilon m. So here we may write this is greater than m into epsilon k. Let epsilon k is epsilon by 3m. It is our choice. So here m cancel. This is epsilon by 3. Therefore S1 less than epsilon by 3. Let this is 11. By using 6, 10 and 11 we get modulus of fz plus h minus fz by h minus gz less than S1 is less than epsilon by 3, S2 is less than epsilon by 3 and S3 is less than epsilon by 3 and this is epsilon. We put the value of gz, this sigma n equal to 0 to infinity n an z to the power n minus 1. We may write this as limit h tends to 0 f z plus h minus fz by h equal to sigma n equal to 0 to infinity n an z to the power n minus 1 which is gz. This relation shows that fz has a derivative gz. Since fz is one valued function and is also differentiable in modulus of z less than r, therefore fz is analytic in modulus of z less than r. So our theorem is proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.